Hello, my dear students and the rest of the learners. Welcome to this presentation in which we are going to learn about memory management in operating systems with our focus being on segmentation memory allocation technique. This is part 8 of a 9-part series of presentations and videos on the topic memory management in operating systems. My name is Meme JM, or you can simply call me Emily Swap. In this presentation, we are going to look at segmentation under the following aspects. We shall look at introduction to segmentation, application of segmentation, marking or mapping segmentation address to physical addresses, steps for address translation, types of segmentation, and finally, we shall look at the advantages of segmentation. Segmentation is a visual memory management scheme in which a user program and its associated data are subdivided into a number of dynamically varying and equal-sized blocks that resides in memory, in secondary memory, and loaded to RAM during execution. A segment is therefore a variable length block of data that resides in secondary memory and may be temporarily copied into an available region of main memory, either as a whole or may be divided into segments which can individually be copied into main memory, where we have combined segmentation and paging. Segments are areas of memory that usually correspond to a logical grouping of information such as a code procedure or a data array. Segments require hardware support in the form of a segment table, which usually contains the physical address of the segment in memory, its size, and other data such as access protection bits and status, swapped in, swapped out, amongst other types of status. Therefore, one way of freeing the programmer from having to manage the expanding and contracting tables in the same way that visual memory eliminates the worry of organizing the program into overlays is to provide the machine with many completely independent address spaces that we call segments. Each segment consists of a linear sequence of addresses from 0 to some maximum. The length of each segment may be anything from 0 to the maximum allowed. Different segments may, and usually do, have different lengths. Moreover, segment lengths may change during execution. Segments are also used to implement protection schemes. The segment table contains details of the memory allocated to each program. So when a program tries to access a memory location, the memory management unit can check that it is within the allocated space before allowing it to do so. Each entry in the segment table contains protection bits indicating whether that segment can be read or written to by other processes. This allows for the sharing of data between processes. Because of the use of unequal-sized segments, segmentation is similar to dynamic partitioning. The difference compared to dynamic partitioning is that with the segmentation, a program may occupy more than one partition, and these partitions need not be contiguous. Segmentation eliminates internal fragmentation, but just like dynamic partitioning, it suffers from external fragmentation. However, because a process is broken up into a number of smaller pieces, the external fragmentation should be less. Whereas paging is invisible to the programmer, segmentation is usually visible and is provided as a convenience for organizing programs and data. Typically, the programmer or compiler will assign programs and data to different segments. For purposes of modular programming, the program or data may be further broken down into multiple segments. The principal inconvenience of this service is that the programmer must be aware of the maximum segment size limitation. Another consequence of unequal-sized segments is that there is no simple relationship between logical addresses and physical addresses. Analogous to paging, a simple segmentation scheme would make use of a segment table for each process and a list of free blocks of main memory. Therefore, each entry in the segment table has a segment base and a segment limit. The segment base contains the starting physical address where the segment resides in memory, and the segment limit specifies the length of the segment. So, each segment table entry would have to give the starting address in main memory of the corresponding segment. The entry should also provide the length of the segment to ensure that invalid addresses are not used. Segmentation is therefore a memory management technique in which each job is divided into several blocks of different sizes, one for each module that contains pieces that perform related functions. Each segment is actually a different logical address space of the program. When a process is to be executed, its corresponding segmentation are loaded into non-contiguous memory through, although every segment is loaded into a contiguous block of available memory. Segmentation memory management works very similar to paging, but here segments are of variable length, whereas in paging, pages are of equal fixed sizes. A program segment contains the program's main function, utility functions, data structures, and so on. The operating system maintains a segment map table for every process and a list of free memory blocks along with the segment numbers, their size, and the corresponding memory locations in main memory. For each segment, the table stores the starting address of the segment and the length of the segment. A reference to a memory location includes a value that identifies a segment and an offset. The following diagram, therefore, illustrates segmentation. From this diagram, we can see that we have process P, and this process P has been broken down into various segments of varying sizes. We have segment 1, segment 2, segment 3, and any other segment or segment number, segment N. Each of these segments have been placed or have been indicated using or represented using a segment map table, which have been serialized, or the segments have been serialized from serial number 1 to serial number N. For example, from the segment map table, we can see that segment 1 is of size 400 and its memory address is 100. And when you look at the main memory, you can see that from the memory or from the segment map table where segment 1 has been serialized as 1 and 1, we are able to identify that its memory address is memory address 100. And therefore, from there, we are able to trace that segment from the main memory under 100. If we pick, for example, segment number 3, we can see that segment number 3, which is this segment, has been represented in a segment map table where 3 is serialized, segment 3 has been serialized as 3 under the segment map table. And this segment is of size 100 and it can be found from the memory address 800. And therefore, using that address, we are able to trace it. We are able to trace it from the main memory. And then from here, you can see that that is the main memory or the section of the main memory that we are referring to. This is the segment that we are referring to. Therefore, when a process enters the running state, the address of its segment table is loaded into a special register that is used by the memory management hardware. Just as with the paging, a logical address using segmentation consists of two parts. In this case, instead of having a page number, as it is for paging, we have a segment number, which is an identifier or a name, and an offset to that segment relative to the segment base address, defined to be offset 0. If you want to learn more about paging memory allocation method, you can listen and watch video part 6 on paging memory allocation method. Address translation for segmentation is also very similar to that of paging, except that instead of page number, we have segment number, and instead of displacement, we have offset. The desired physical address is the sum of the starting physical address of the segment plus the offset, just as it is for paging. And therefore, the segmentation address is of the form bracket S, comma, O, instead of a bracket P, then comma D, bracket for paging. So this means that S is the segment number while O is the offset. The segment is therefore just a replacement of P, which we came across under paging. And D is a direct replacement, or O is a direct replacement of P, of D. And therefore, this indicates that this is a segment, or it indicates segmentation, or this one is paging. For example, if we have a logical address, 0001, 001, 0, 1, 1, 1, 1, 0, 0, 0, 0, whereby 4 bits represent the segment number, then the segmentation physical address will be tabulated as follows. So you get the segmentation address, the entire segmentation address, which is 0, 0, 0, 1, 0, 0, 1, 0, 1, 1, 1, 1, 0, 0, 0, 0. And then because you have been informed that the 4 bits represent the segment number, we pick the first 4 bits from the higher edge of the address that will represent the segment number, and the remaining bits will represent the offset. So the physical address will be in form of segment number and offset. So pick the bits that represents the segment section and convert this binary digit into decimal equivalent. And when you convert this binary number into its decimal equivalent, you get 1. You do the same for the offset, and in this case, the decimal equivalent of this binary digit or series of binary digits is 752. This means that its physical address would be bracket 1, 752. You enclose that in brackets. That is a segment offset, segment length or size. That is segment offset of 1, and its segment length is of size 752. So this is segment offset or segment length of 752, and it is found on segment number 1. That's another way of interpreting it. This can be represented as follows. From this diagram, we can see that we have our logical address, and our logical address is 0001, 001, 01, 111, 0000. So if we have this logical address, and we know that the 4 bit on the high end represents segment number, then this segment number will be 1, and its offset will be 752. So from this memory, we can see that segment number 1 is 1950 bytes. Segment 0 is 750 bytes. And therefore, our offset indicates that the size that shall be allocated to our segment is 752. 752. So our segment is of the length 752, and it commences at 1. Each segment has a base address and a limit. If the offset is greater than the limit, the address is invalid. Otherwise, the offset is added to the segment's base address, giving the unsegmented address. Segment identifies or identifiers may be implicit. For instance, they may be obtained from a current segment register. So, if we have a system that uses a 4-bit segment number, such as the one that we have looked at, it means that the maximum segment number or limit that it can accommodate is 2, which represents 2 states, 0 and 1, raised to power 4, which gives us 16 segments. In addition, if a system, for example, has an offset of 12 bits, such as the one that we have also looked at, then it means that the maximum segment size or limit would be 2 to power 12, which is 4 kilobytes, or what is equivalent to 4096 bytes. My dear students and the rest of the learners, it's important to note that 1 kilobyte is equivalent to 1024 bytes. And therefore, when we talk about 4 kilobytes, we are simply saying it is 1024 times 4, which gives 4096 bytes. This means that the maximum segmentation physical address for the above system would be 16 segments, each being of size 4 kilobytes. Therefore, a program can consist of a maximum of 16 pages of 4 kilobytes each. Therefore, valid segments will be 0 to 15, and the valid segment lengths will be 0 to 4095. Any addresses beyond any of these values will be invalid. This means that with a segment size of 4 kilobytes in a 16-bit system, an offset field of 12 bits is needed, leaving 4 bits for the segment number. The size of the segment is stored in the segment descriptor and compared with the segment offset. The segment descriptor contains the physical address of the start of the segment. Therefore, if we have a logical address of n plus m bits, where the leftmost n bits are the segment number and the rightmost m bits are the offset, the following steps are needed for address translation, or what we call segmented address reference. And just to remind you, my dear readers, listeners, or my fellow dear students, I would still like to remind you to listen to the video part 6 of 9 that discusses paging, so that you can improve your understanding on segmentation, because the method of translation is the same. So just as we did for paging and that video part 6, this procedure is the same. So what you do, the first step is to extract the segment number n and the offset m from the logical address. So if, for example, we have a 16 or an 18 visual address for a system, and then we are informed that, for example, 6 bits represent the segment number, that is n, then to be able to know the offset, what you do is get the 18 bits, subtract the number of bits that represent the segment number, for example, 6. And therefore, the offset, which is m, will become 18 minus 6, which gives you 12. And therefore, the segment number will be 6 bits, while the offset will be, m will be 12 bits. Second step is You use the segment number as an index to the process segment table to obtain the segment-based address, that is the starting physical address of the segment, and the length, or what we call the segment size. For you to be able to get this index, you need to convert the binary digit for the segment number and convert it to its decimal equivalent. And then from the process or segment table, you use the value you will get as an index, which then you are going to use to be able to identify the specific segment, or like what we are calling frame segment in the physical memory. So number 3 is check that the offset is not greater than or equal to the given length. If so, the address is invalid and an invalid address is signaled. Number 4 is to generate the required physical address by adding the offset to the base address. When a particular process is running, a register holds the starting address of the segment table for that process. The segment number of a virtual address is used to index that table and look up for the corresponding main memory address for the start of the segment. This is added to the offset portion of the virtual address to produce the desired real address. Therefore, the segment number is used, just as I have said, as an index to the segment table. The offset of the logical address must be between 0 and the segment limit. If it is not, we trap to the operating system because the logical addressing attempt is beyond the end of segment. When an offset is legal, it is added to the segment base to produce the address in physical memory of the desired byte. The segment table is that initially or essentially an array of base limit register pairs. When a relative address is encountered, it is added with the content of the base register, that is the location register, to obtain the physical address, which is contained with the content of the bound register. The value in the base register is added to every address generated by a user process, which is treated as offset at the time it is sent to memory. For example, if the base register value is 10000, then an attempt by the user to use address location 100 will be dynamically reallocated to location 10100. So suppose that the segment 00101110000 from the logical address that we have already looked at is residing in main memory, starting at physical address 00100000001 00000. What will be the physical location or address for this segment in memory? For us to be able to get this physical location or physical address, what we do is we get the first address and then we add it to the second address, that is 0010, then 00000001 00000 plus 001 01111 0000. This will give us 001 00011 0001 0000. My dear student and the rest of the learners, for you to be able to know how to do the number conversions, like binary additions and the rest, I would advise that you keep on checking the YouTube channel by the name MLSwap ICT for a video by the name Data Representation in Computers, which will teach you and equip you with knowledge about number conversions and number representations. So this logical to physical address translation can be represented as in the following diagram. So from this diagram, you can see, my dear student and the rest of the learners, that we have a 16-bit logical address, whereby we have the 4-bit segment number, which is 0001, and then the rest is an offset, or what we are calling underpinning displacement. Then what we do to be able to get the physical address is from the logical address for the segment, we pick the offset, or in other words, we pick the 4-bit for the segment number. In this case, is 0001. Then we convert it to its decimal equivalent, which gives us a 1. From there, we use that 1 as our index in the process segment table. So we come to the index number 1. From there, we read the content in that page table. That is the length part and the base part. Once we do that, we then pick the length and the base that we have been able to trace or access from our process segment table. We replace that then with our segment page, and therefore we maintain or retain our offset. But then in this case, you know, that's what we were doing under paging. But in this case, what we do is we pick. What we do in this case is we pick the base that we have gotten. We add it to the offset that we had from our visual or logical address. Once we do that addition, then we are able to get this address. So we pick the offset for our visual segmentation address. We pick the offset, we add it to the base. And once we do that addition, then we are able to generate a physical address, which in this case is or will be our 16-bit physical address. The following diagram illustrates the address translation in a segmented system. So from this diagram, we can see that we have the visual address, which has a segment number and an offset, or what we usually call displacement under the paging. So we pick the segment number, we add it to the segment table pointer. Once we add, whatever we get, we use that to be able to move to our segment table. And we use what we have gotten as the index to give us the length and the base of our segment. Then we pick the offset. We pick our offset. We pick our offset and we add it to the value we have gotten from the segment table as the base. So we add the two. Once we add the two, we are able to get the physical address for our segment, which will be the value we have gotten for the base plus what we had as our offset from the visual address. And with that, we are then able to move to the main memory using the physical address, and we are able then to trace or access the segment of main memory that is of our interest, and we are also able to know how big that segment is in terms of its displacement. An example on how we do the computation is as follows. If a system has, for example, the following logical address 000001 01 11 01 1110 with a segment size of 1 kilobyte, then this is how we move on. The question is, how many bits will represent the segment number and the offset field? So what we do is we get the segment size, which is 1 KB. We convert it into its equivalent bits, which gives us 1024 bits, which is equals to 2 to the power 10. And therefore, our offset will be 10 bits. Will be 10 bits. Because logical address are 16 bits, then the segment number will be 16 minus 10, which will give us 6 bits. That will give us 6 bits. Number B, what will be the relative address for the above segmentation address? To be able to get that, we compute the decimal equivalent for the logical address 0 0 0 0 0 1 0 1 1 1 0 1 1 1 1 0, and from there we are able to get equivalence or a decimal value of 1502. And therefore, once we have gotten our decimal equivalent of 1502, we can then be able also to proceed and find out the corresponding physical address for the relative address that we have already calculated. And for us to be able to do this, we compute the binary equivalent of 1502 to get the logical address. So simply what we are saying, my dear students and the rest of the learners, is that we are supposed then to convert the decimal number 1502 to its binary equivalent. Then we organize the logical address as the segmentation address in the form of S, O, we enclose that in bracket, whereby S, in this case, will be 6 bits, and the offset will be 10 bits. Therefore, our segmentation address SO will be equals to 0000001, 0111 0, 1, 1, 1, 1, 0, which will yield 16 bits. So after you convert 1502, then number of bits that we are going to get, if they are not totaling to 16, we add some additional zeros on the high underside of our address. So we add a certain number of 0 bits on this higher side, so that then we are able to get the total number of bits that are required. From there then, we compute the decimal equivalent of for the segment and for the offset. And then we organize the values in form of physical address, SO. This will give the physical address of bracket 1, 478. We close the bracket. That is an offset of 478 on segment 1. Number D, which will be the valid segment numbers and segment sizes in this system. That is limits for segment identification and segment length. The solution is get the segment number. The segment number we have seen is 6 bits. So get 2 raised to the power 6, which will give us 64 segments. And then we know that the segment size is equal to 2 to the power 10. That gives us 1024 bytes, which is equivalent to 1 kilobyte. And therefore, this means that we are going to have 64 segments of 1 kilobyte each. Segmentation violation occurs when an attempt is made to access memory whose address is well formed, but to which access cannot be granted. This might be due to either a protection fault or an invalid segment fault. There are 2 main types of segmentation. These are simple segmentation. That's one example of the type of segments or segmentation, simple segmentation. This is a memory management scheme whereby each process is divided into a number of blocks that need not be of equal size, and the process is loaded by loading all of the segments into dynamic partitions that need not be contiguous. In this case, each process has its own segment table, and when all of its segments are loaded into main memory, the segment table for a process is created and then loaded into main memory. Each segment table entry contains the starting address of the corresponding segment in main memory, as well as the length of the segment. The second type of segmentation is called visual segmentation. This is a memory management scheme whereby each process is divided into a number of unequal-sized blocks that are retained in the secondary storage medium and are loaded into memory later as the process continues with execution. Therefore, in this scheme, it is not necessary to load all of the segments of a process. Non-resident segments that are needed are brought in later automatically. Because only some of the segments of a process may be in main memory, a bit is needed in each segment table entry to indicate whether the corresponding segment is present in main memory or not. If the bit indicates that the segment is in memory, then the entry also includes the starting address and length of that segment. Another control bit in the segmentation table entry is a modified bit, indicating whether the contents of the corresponding segment have been altered since the segment was last loaded into main memory. If there has been no change, then it is not necessary to write the segment out when it comes time to replace the segment in the frame that it currently occupies. Other control bits may also be present. For example, if protection or sharing is managed at the segment level, then bits for that purpose will be required. The following are therefore the main advantages of segmentation to the programmer over a non-segmented address space. Number one, it simplifies the handling of growing data structures. If the programmer does not know ahead of time how large a particular data structure will become, it is necessary to guess unless dynamic segment sizes are allowed. With segmented virtual memory, the data structure can be assigned its own segment, and the operating system will expand or shrink the segment as needed. If a segment that needs to be expanded is in main memory and there is insufficient room, the operating system may move the segment to a larger area of main memory if available, or swap it out. In the latter case, the enlarged segment will be swapped back in at the next opportunity. Number two, it allows programs to be altered and recompiled independently without requiring the entire set of programs to be relinked and reloaded. Again, this is accomplished using multiple segments. Number three, it lends itself to sharing among processes. A programmer can place a utility program or a useful table of data in a segment that can be referenced by other processes. Number four, it lends itself to protection. Because a segment can be constructed to contain a well-defined set of programs or data, the programmer or system administrator can assign access privileges in a convenient fashion. Segmentation, therefore, allows better access protection than other schemes because memory references are relative to a specific segment and the hardware will not permit the application to reference memory not defined for that segment. With the segmentation scheme, there is still a possibility that there is insufficient memory available to load a segment. This can be overcome by a combination of segmentation and paging, whereby each variable length segment is composed of a number of fixed length pages and has its own page table. In a combined paging versus segmentation system, a user's address space is broken up into a number of segments at the discretion of the programmer. Each segment is in turn broken up into a number of fixed size pages which are equal in length to a main memory frame. If a segment has length less than that of a page, the segment occupies just one page. From the programmer's point of view, a logical address still consists of a segment number and a segment offset. From the system's point of view, however, the system offset is viewed as a page number and page offset for a page within the specified segment. Congratulations for viewing and listening to this video on segmentation memory allocation technique, which is part 8 of memory management topic. You can listen to the other parts of memory management topic as well as other videos in the field of ICT versus computers from Emily Swap ICT YouTube channel. In addition, for you to be able to access free life skills, motivational and inspirational resources, you can visit Emily Swap Motivation YouTube channel. I would also request that you subscribe to both channels in order for you to be able to receive immediate updates whenever a new video is posted in any of them, if you have not already done so. For any further correspondence, kindly write to us through the email emilyswap@gmail.com. Thank you very much for listening to me and be blessed.